energy balances. Let's wrap up with the rate of energy by convection. Okay, there we go. Please let me know if you see anything else, but I believe you are seeing the notes on heat transfer by advection. I said convection, but I actually meant advection. Here we go. And view. Awesome. There we go. So what we're talking about is exactly the same thing we've been discussing so far. Q in minus Q out plus Q generated equals Q stored. Now, because we're talking about rate, we're talking about small Qs, those measured in watts. Trivial to some extent. But if we put it, if we apply it to what would be one tube in a heat exchanger, interesting things come up. And we start the same way we always start. And it is by writing, doing a control volume and an energy balance. So let's see. We said, here we have our control volume. Interesting. She's not annotating, but if it doesn't start working soon. Okay, here we go. Resume share. I think that's what's going on. Yes. Okay, here we have our control volume just inside the pipe, and we're indicating the fluid, whether it's water, whether it's air, whatever it is, no problem, can be oil. And the balance of energy is the one we always do. Q in minus Q out plus Q generated, Q stored. So you realize that so far, this class is ridiculously mechanical. The trick is what we build on top of this mechanism. So we're gonna go one step at a time, and we're gonna say, okay, what is Q in, what is Q out? And let's look at, first of all, let's see what is zero to make it easy. Let's say there's no heat generation in this case. I typically talk about radioactive things because they have volumetric heat generation. In the case of fluids, the viscosity is energy that is dissipated. In what form? In the form of heat. Now, the amount of heat dissipated by viscosity is typically small. And I'm not proving that to you now. I'm assuming that, and I hope you believe me, is not always the case. If the fluid is moving very, very fast, that viscous frictional heating can end up being relevant. The beauty of these equations we're writing is that we can account for it if we want it. Right now, because we're taking baby steps, I'm just telling you, no, there is no viscous heat generation. But we can prove it that later on. So no heat generated. And here is a very important concept, the concept about heat stored. And we saw that heat stored meant a temperature increase or a temperature decrease. But in this case, we in the heat exchanger is running in steady state. So we're gonna say no heat stored. Something that might be interesting too, this system, when you look at, when we first discussed control volumes, I used two words and they're in the notes, and I'm updating the notes so this is more clear. I use the words Lagrangian or Eulerian. That is kind of seldom matters, but this is one of those times in which it matters, because this, let's say, is water that is flowing through this pipe, and if it is at temperature T1 here, and then it's at temperature T2 here, this piece of this a little bit amount of water that is moving is either heating up or cooling down, right? From that point of view, you'd say, hey, if the water is heating or cooling, therefore you have a change in time, right? That is if you're using the Lagrangian formulation in which you move with the fluid. However, there's a smarter way of doing it in this case, because if we say our control volume is fixed and the water comes in one end and out of the other end, and we're always looking at the same control volume, we don't see any changes with time, right? In this case, the control volume is fixed and the fluid just goes through the control volume. Okay, I have a question here. Q stored 0 for all steady state system. Correct. Q stored is 0 for all steady state systems. And the reason is you can prove it mathematically. We said that Q stored, let's go. First, let's erase this. Okay. We said that Q stored in an open system, here we have in an open system, the Q stored is the variation of mass with a enthalpy over time, right? And in this case, when we have advection, that is what we have here, is m dot times I, right? And this is what gives us the, so hold on, we have to go even earlier. Well, I'm making a mess, but yeah, oh, here we go. Q stored, well, this is a closed system, so it doesn't help. So the bottom line is, yes, Q stored is 0 for steady state systems. So let's move on. But right after this class finish, we're gonna have office hours, so we'll have more time to fumble and do it properly for you. So you can stay, but let's move on with this we were discussing. So now we had this energy balance. We said no heat generation. We said because the system is in steady state. Seminar started last Friday. We are going to have a seminar, and that's in the notes that are already uploaded since the beginning of classes. So we're going to have a seminars start today at the usual hour. Not last Friday. This start today. Yes. And so we have to see what the heat coming in is, and the heat coming in is heat that is coming in, say the fluid is cooling down. So we have this fluid coming in with at a mass flow and a temperature, and this will be our heat coming in. What is going out? Well, the fluid is going out at temperature T2, that in this case is lower, but in addition, we have another heat loss through the wall of the tube. At this stage, I'm not saying if it is conduction, I'm not saying if it is convection, I'm saying nothing. I'm just saying there is a loss, and this is all we need to know at this stage. And so if we put all these equations together, Q in, that is m dot times I1, right? And the one for Q out. When we replace all these equations into equation 73, and we do our balance, it results that we can calculate the heat losses. That is mass flow times the variation in enthalpy. And this equation, number 76, that is valid even if we have phase changes. No problem at all. Oh, let me get this. Now, if we don't have phase changes, right, the enthalpy is proportional. The enthalpy variations are proportional to temperature variation. So we can replace the delta enthalpy by specific heat times delta temperature. And with this, which is the case of heat exchangers that are traditional one, not condensers and not evaporators, a normal heat exchanger, this equation is going to be one of the equations of design of a heat exchanger. It's amazing. I was hoping to do this on Friday, but we're doing it on your fourth class. You already know how to start calculating heat exchangers. So I'm going to go over this example that is in your notes, and I just work it out to see how we would start thinking of the design of a heat exchanger. So it says that in a heat exchanger, we want to cool 1 liter per second of water at atmospheric pressure, right? That goes from 70 degrees C to 40 degrees C. So I know that water at 1 atmosphere between 40 and 70 degrees is liquid water. It's not going to evaporate. It's not going to freeze. And the question is, what is the duty in kilowatts of this heat exchanger? So interesting first practical definition in this class. Duty of a heat exchanger. The duty of a heat exchanger is how much the power of heat transfer it has, right? How many kilowatts can this heat exchanger transfer, right? It's somewhat like you measure like car engines in horsepower, right? Like you measure heat exchangers in the duty. And the duty is always positive because it means how much heat is exchanged. So that's a number that says how much heat went from the hot fluid to the cold fluid. Okay, so in this question, we could do the whole energy balance, but we don't have to because we already have this other equation up here. And let's put it to good use, right? That is asking us how much heat the hot fluid lose. That's the definition of duty. Okay, Q loss. This is a type of formula that in the closed book exams would be in the formula sheet. Your exams are going to be open book. If you wish to have a formula sheet, the formula sheets we have prepared in previous years are uploaded in the with the past exams that we have uploaded as an example. Feel free to use them or make your own. Just have the book or you Google it. The one thing you cannot do during the exams is to communicate with other people. But all the rest, fair game. All right. So the mass flow is density times volumetric flow or specific volume. And in this case, I'm suggesting how to navigate the book to get the properties. And I'm suggesting here what tables you can go. And I would really suggest that you do it, because if you can do this one, you're already half the way of calculating heat exchangers in your next work assignment, your next internship. All right, so in this case, we would have replace the values, and we would have that 1 liter of water per second that goes from 70 degrees to 40 degrees is 123.5 kilowatts. That's awesome, because now we need we know how much power we need. Now we know how much power we need. We're only halfway to calculate heat exchangers, because we don't know if for 123.5 kilowatts that's a small heat exchanger is a huge heat exchanger. You don't know that at this stage, but you will know it very soon, right? The other interesting thing is to calculate the duty. I didn't say if it is a shell and tube. I didn't say if it is a compact heat exchanger. This is just an issue of energy balances. Later on, we're going to see that depending on the configuration of the heat exchanger, what the size or other the calculations for size would be, right? I hope you're impressed, because with the little you learn already, you can say very important and practical things. I'm going to switch to heat transfer mechanisms. And if you have any questions, you want to put them on the chat, and I'll try to address them while we change.